Thank you very much for the invitation and thank you all for coming here, virtually or physically. So we will be talking about it. I will briefly. So this is the entire tutorial about deep learning on graphs and our library. We have a library called DIG, Dive into Graphs. So this is a library developed in my lab. We will proceed it like this. So I will do a very short introduction. Then my students will. So the entire session will be. We will talk about two topics. One is if you have a graphs in 3D space, how do we learn representations of the graphs? Then we will talk about graph generation. So the first one is more prediction. So if you have graphs, how do you make predictions out of the graphs? The second part is more generation. So if you have some graphs, just like image generation. So and how do you learn the distribution over the graph data and then how to generate new graphs? Okay. Then after that, there will be a handout session. We will have a handout session to demonstrate how to use our DIG library to do these two tasks. Okay. So I will start with a very short introduction. So graphs basically capture. So if you have a real world object, etc. So in many cases, a graph is the natural data structure to capture your objects. Like if you have, for example, if you have a social networks here, each node is an individual, then you relationship between individuals can be captured by, for example, if people A send an email to people B, then there is some connection, etc. So we have a social networks, and for example, if you have a molecular graph, so if you have a molecule, basically each node here is an atom, and then there are chemical bonds between the atoms, then you have a graph. But this graph slightly different with the other one. So we are more interested in this type of scientific graphs. So I will tell you what's the difference. Then, for example, you can have a document networks here. So each node here, you can represent each node as, for example, a scientific paper. Then the citations, if this paper cite this paper, then there is a page. So and you also can have brain networks. So our research in general graphs like this, and we do some research on this type of graphs and a lot more on this type of graphs. Okay, so today I think we will talk about both, but more on the graphs in what we call this. Some people call this 3D graph, some people call it geometric graph. Basically, you not only have the relationship, but each node has a location, the spatial coordinate in 3D space. So that usually the geometry of this graph is also important. In the social network, so you won't be too much interested if this person is at a location. For example, college station, this person is in Texas, in Houston or not. You are not much interested in the location. Because if I send an email, it doesn't matter too much if I send an email to somebody in Houston or Dallas. Yeah. So the type of problem we can work on, I think these are some examples. So you can either do a node level classification. For example, if you have a document network, so for example, this you can make a prediction out of each node. So I want to predict the scientific discipline of each of these paper that belongs to. This is physics, this is computer science. So I have a prediction for each node. I can also have a prediction for each graph. For example, in this molecular representation learning problem. So this given this molecule, I can try to predict a label for this entire graph. For example, I think people have actually used machine learning to identify a new antibiotic purely using computation. Identify antibiotic. In that case, your input is a graph, your prediction is just a binary label, but yes or no, antibiotic or not. So that is the graph level prediction task. We can also do link prediction. Obviously, we want to. So, for example, we can in social network we want to predict if there is going to be a link between the two persons or not. So, and we can study other problem like generation and explainability. So in generation, like I have, so we will talk about this today. So if you have some molecules and you want to generate a new molecule that follow the same distribution, and we can also do property optimization. We want to generate a molecule in same distribution, but it has certain desirable properties of that molecule. And we also can study explainability. So you can make predictions for certain molecule. For example, if I predict this molecule can be used as antibiotic, I think the domain experts may be interested to know, so which part of molecule actually is very important to determine that particular level, so that they can try to explain. So the general paradigm of graph neural network is this message passing. So basically, you have input as a graph, then each layer you will apply these two operations to basically pass the message from a neighbor over this node. For each node, you will basically compute. So I think our basic idea here is that our graph is attributed. So we have a graph, and each node is associated with the feature vector. And this is our input, and each layer of processing basically will update the embedding of each node based on the neighbors. So, for example, here, H here represent the hidden representation of node U at layer L-1. So to compute these two steps basically compute HU L-1 to HVL. So you can see after each layer, so this layer index increased by 1. So we do a layer-wise message passing. So in each layer, there are basically two operations. First one is this is basically aggregate. So to compute a message from the L-1 to L, basically you aggregate the message. So to compute the representation of node V, you consider all the U's which is unused neighbors of V, and you take all their representations. So basically, in each layer, to compute the message, you basically take the hidden representation of the neighbors of that node from the previous layer. So you get a VL, and then you update to get an HVL by considering this message and the previous hidden representation of that particular node. Okay, so that's it. Basically, you can write this in single equation, but just for clarity, we first aggregate the message, the representations of the neighbor, then we also do an update. So we are very interested in these geometric graphs or 3D graphs, just because in scientific disciplines, many of these graphs are actually in 3D. Their geometry is very important. So if, for example, you study small molecules, if you study drug discovery, you basically study small molecules. And the geometry of these molecules are very important because drug actually works by docking to a protein or to another molecule. So this is basically like a key and lock. So the 3D shape is very important in molecular interactions. Just like similarly for protein and crystal structure, the material, in all of these, I think the 3D structure is very important. So fundamental problem is 3D graphs, geometric graphs compared to the regular graphs without 3D is this something called invariance and equivariance. So these are this problem. I do not think that they are so important in regular graphs, but in 3D graphs they are very important. So basically, this means if you have, for example, if you have a molecule. So this is a physical update. So whenever you have a molecule here, so the nature does not have a coordinate, right? So I move this molecule here. If I rotate, etc., the molecule remains the same. But as long as you represent it into a computer or into some kind of representation, you have to use a coordinate, right? You have to use a reference frame. So then the problem becomes if I rotate, if I move my molecule, for example, my object, any physical object, then your representation, your coordinate, so it will basically be if you fix your coordinate, if you move this, your representation will change, right? But your final deep learning outcome should not change, should not depend on any coordinate. If I have molecule, it is antibiotic. If I move here, it will be the same antibiotic, right? The property will not change. So this is the.
I have a question. So you said that the graph is used to describe a relationship. So for this examples you give here, right? They are 3D graph, but you project it to 2D. Are they still pretty much describe the same relationship?
I think the relationship is, yeah, in general, I think in regular graphs it captures relationship, but in geometric graph it not only capture relationship, but also capture the geometry, the relative positions. So, for example, if the angle between two bonds, if I have I have atom here. So in general graphs, so for example, if I have two neighbors, the two neighbors, their relationship may not be important. For example, what's the angle between the bonds between this neighbor and this one and the neighbor, these two neighbors? The angle may not be important, but in geometric graphs, these are important. So basically, in this geometric graphs, it's not only the object and relationship, but also the geometry. So this is something called invariant. Basically, if you change your input, something will not change. Basically, the property will not change. So that's called invariant. And another one is equivariant. Basically means if you try to, for example, predict node-wise property. For example, if you try to predict the velocity. In molecular dynamics, we try to, for example, try to predict the movement of each atom. And then you need to predict the velocity. Velocity now is a vector, right? If you rotate, for example, if you rotate your molecule, the velocity is a vector for each node. The velocity is also rotate. Right? Yeah.
So this related to doing some sort of Procrustes solving, trying to minimize the distance.
Yes. Yeah. So this is what we do in molecular dynamics. We try to predict, for example, the velocity of each node. Then if you do that for each point, you basically got a trajectory how the molecule will move. So in that case, you're making a vector prediction for each node. And if you, for example, rotate a molecule, that vector should rotate correspondingly, right? So that's called, so something will change, but the change correspondingly. So that's called basically equivariance. So how to achieve this invariance and equivariance? So that's, I think this kind of problem may not exist in regular graphs, but it's very important in geometric graph. Because otherwise, the underlying physics has changed. If I have a molecule here, and I can predict this is the antibiotic. If I rotate or move it here and then become a totally different prediction, then this doesn't obey the physical law. So the other thing would be like a completeness efficiency. Completeness basically means if I have two different molecules, two different geometric graphs, okay, then can you guarantee that your representation will remain different for two different inputs? So that complete basically means if you capture the complete 3D information, then if your input changed, your deep learning representation would also change. So the representation basically will be distinct for distinct molecules. And then I think there is some kind of trade-off. If you try to make it complete, then you need to capture in each step, you need to capture more information. Then there is a problem of efficiency. Then if you do complicated calculations in each step, then you might run into a little bit of efficiencies. So so how can we achieve completeness without sacrificing too much of efficiency? Is also a question. Okay. So next I will turn to Lili, and we will talk about the representation learning part of 3D graph. Basically, given a geometric graph, how can we learn a representation? Okay.
Basically, I will introduce some invariant 3D graph neural networks and some equivalent graph neural networks, and I will also discuss the completeness and the efficiency of some of these methods. Firstly, a very famous invariant 3D graph neural network. This method tries to incorporate distance information between nodes. Basically, if we the geometric distance between nodes, then we can somehow incorporate the 3D structure information. And the message passing scheme they used is for each node I, we use all its neighbor nodes G to update the features on the node I, and this update includes the feature of this node G and the distance between node I and G. In this way, this method can incorporate the distance, also incorporate the 3D information into the graph neural network. And specifically, distance is a value between two nodes. We can use some functions to embed this distance value to a feature vector. And the commonly used function is called the radius basis function. Basically, as shown in the figure, we have 4 basis functions. Then for each input distance value, we can embed this value to a 4-dimensional feature vector. In this way, we can embed the distance value to a feature vector and then incorporate the feature vector into the graph neural networks. But the problem of this method is that it's not complete. As shown in the figure, the first 2 examples share the same distance values, but the 3D geometry of these 2 examples are different. Therefore, this method is not complete. But how can we make it complete? We can simply consider more edges. As shown in this example, if we further consider the distance between the 2 yellow nodes, then we will know that these 2 examples are different 3D graphs. Therefore, if we consider more edges, basically if we are using a fully connected graph, consider the connection between every pair of nodes, then we can achieve completeness. But in this way, the method will become more complex. Therefore, there's a trade-off between the completeness and the efficiency. Following this method, another work called TAMIDS, this method tries to incorporate both distances between nodes and the angles between edges into the graph neural network. The message passing scheme of this method is, as shown in this figure, to update the message or to update the information on this edge from G to I. We are considering all of these neighbor nodes P, basically to update the message on edge GI, we are reading the message on edge KG and all of these 3 angles and the 3 distance values. And similarly, this method also uses some basis functions to embed the distance values and the angles. So in the bottom figure, the first one is the basis function to embed the distance. For example, here shows 5 basis functions. Then we can use this basis function to embed one distance value to a 5-dimensional feature vector. And the right figure shows the basis functions to embed both distance and angles. This figure shows 16 bases, basically for each pair of input. The input includes a distance value and an angle value. We can output 16 dimensional feature vector for this input. And finally, we use this embedded distance embedding and angle embedding to update edge features and finally update node features.
Yeah, and just add on what Limi said, I think the key of this is the SHUNet or SCHNet. In previous slide, basically, when you pass the message from node 1 to node B, basically you consider the distance between this. So in regular graph, when you have a node, you pass the message from neighbor to this node, you do not consider the distance, right? So you just whoever is the neighbors, they will just pass a message. So in this SHUNet or SCHNet, basically you in the message passing function, will you make use of the distance? If these two nodes are further away versus closer, the message, although the message will be same, the embedding will be same, the message will be different, because I think if somebody is closer, the message will be different with someone that's further away. And this DimeNet basically not only consider distance, but also consider the angle. For example, if you pass a message here from I think if you pass message from other neighbors to J node, so what is the angle between, for example, this node Ki, this node Ki the I? So their angle, what's the angle? If I pass a message from AB to C, what's the distance? What's the angle between this CA and CB edges? So the angle will be also important. And so I think that's number one point. Number two is what Limi mentioned is a basis function. So if you know the distance, are you going to use the distance or the angle directly in the message, or how are you going to use it? I think this is what we call this the basis function. Basically, what we did is you will not use the distance number directly, but you will pass. But you will have basis function. That function will take this distance and or angle as input and produce some vector as output, and that vector will be used in the message pass. You do not necessarily use the angles or distance raw number directly, but you have a function on top of that. Then you use the function output and function in the message pass. And usually the basic function captures some kind of physics. Like in physics, we use different radial basis function and different functions.
However, this method is still not complete, although it already incorporates distances and angles into the graph neural network. For example, actually in this figure, we only, for one neighbor, this P1, we only consider the angle P1, G, and I. But this neighbor P1 can rotate along the edge GI. And this method doesn't capture this rotation. Therefore, the relations of the neighbor nodes P are not captured. You can see this P1 can rotate along SGI, P2 also can, and the P3 also can rotate along this SGI, and the relationship between these three neighbor nodes are not captured in this method. Therefore, it's still not complete. Next, I will introduce some methods that are complete and also efficient. Firstly, let's consider a local graph. Let's donate a local graph as a central node I and all of its neighbor nodes. Then for this center node I, we can define a local coordinate system. And if we use spherical coordinates, we can represent the relative position of each neighbor node. As shown in the first figure, as long as we have a local coordinate system, we can use the spherical coordinates, this length of this vector d, and the angle theta and the angle phi. We can use these three values called spherical coordinates to determine the relative position of the node. We can determine the position of this node relative to the center node. In this way, we can only determine the relative position. And following this idea, we propose a method to find the local coordinate system and to incorporate the spherical coordinates, as shown in the right figure. In this local graph, we have central node I, and it has several neighbor nodes. We call the nearest one as F1 Fi, and the second nearest neighbor as Si. Then using Fi and Si, we can define a local coordinate system, the X, Y, Z axis for this local graph. After having this local coordinate system, we can use spherical coordinates to fully determine the position of each neighbor nodes. Therefore, in this way, we can fully capture this local graph. And in the paper, we call this local completeness. We have two local completeness in this way. And the next question is, what's the relations between local graphs? In this example, we have two local graphs. One is centered in node I, another one is centered in node J. And there's another degree of freedom we need to capture between these two locals in the rotation angle of the edge IG. You can see these two local graphs can rotate along the edge IG. And if we can further capture so rotation angle, we can fully capture the relations between local graphs. And in this way, we can achieve global completeness. The comparison scheme for this method is to update the features of node I. We are considering all its neighbor nodes J, and the position of this node J is determined by spherical coordinates d theta phi and the rotation angle of the edge IG. And in this way, we can achieve a fully complete method. And all of this method I have introduced are invariant 3D graph neural networks. And basically, all of these methods try to convert 3D position information into distance and angles into such invariant values, and try to incorporate these distances and angles into the graph neural network. And the learned node features and maybe graph features are also invariant, since all the input to the graph neural networks are invariant to the rotation and translation. Then the question is, can we consider the 3D position as, can we directly consider the 3D position as node features? And if we can, then we can somehow define equivalent networks and learn equivalent features for some specific tasks. This comes up the equivalent graph neural networks. In equivalent graph neural networks, for each node, we learn both invariant and equivalent features. The equivalent feature is the difference compared to the previous invariant methods. Actually, in the figure, there are 4 nodes here. For each node, we learn an invariant feature H, and then we also learn an equivalent feature V. And with this equivalent feature, we can predict some equivalent properties like forces, velocity, etc. And the main challenge of equivalent 3D graph neural networks is how can we maintain the equivalence? In other words, what operations can we use to update the features? This figure shows what's the meaning of equivalence. For example, the left part shows the input and the output a graph neural network. You can see this neural network updated the both invariant feature H and the equivalent feature V. The input and the outputs are different. And if we rotate or translate this input graph, the equivalent features also rotate accordingly, and then the output of the network should rotate accordingly. And this is the important property called equivalence. And equivalent graph neural networks should use carefully defined operations to maintain such equivalence. Here is an example, a simple example that can maintain the equivalence. Let's see this formula. The first and the third and the last lines are the basic original graph neural networks. Update node features based on different nodes. And the main difference of this method is that it will also update equivalent features. Specifically to update the equivalent features of this node I, it will consider all its neighbor nodes, and this information includes equivalent part and an invariant part. Basically, if we use an invariant feature to multiply with the equivalent feature, this part is still equivalent. Therefore, we can use this operation to update equivalent features and maintain the equivalence we want to. This method uses this simple operation to update equivalence, and in some following work, we also summarize the operations that can ensure equivalence. The first one is scaling of vectors. The first operation is used in the previous paper, and the second one is linear combination of equivalent vectors. This is also very simple, as shown in the figure. We are given 3 equivalent vectors, and we can use learned weight to do linear combination of these input vectors, and the output is also equivalent. And the other operations include the scalar products and vector products. And all of these operations can ensure equivalence, and most of existing equivalent methods are restricted to these operations. And finally, I will show some applications on proteins. Basically, proteins are very large molecules, and it's very important in various applications. A protein may contain hundreds or even thousands of amino acids, which is pretty large, and each amino acid contains a detailed inner structure. As shown in the figure, this figure shows an example of 5 amino acids, and the nitrogen, alpha carbon, and carbon atoms in each amino acid forms the backbone of a protein, and then the other parts is the side chain of each amino acid. And basically, we want to use 3D graph neural networks to learn repetitions for a given protein structure, and therefore we want to capture some geometric information such as the nitrogen, carbon, alpha carbon, and carbon atoms, and the side chain structures. There's an invariant 3D gene which can fully capture the geometric information. Basically, this method also compute some distances and angles. And then incorporate these distances and angles into graph neural networks to capture the geometric information. And another method is an equivalent method. This method tries to learn both invariant and equivalent node features. The main difference between this equivalent one and the invariant one is that this equivalent method for each node and edge in the graph, it contains both scalar features and vector features. And then they use graph neural network to update both node and edge features. And they only use the operations that can maintain invariance. Therefore, this method can predict some equivalent properties. So, do you have any questions about this invariant methods and equivalent methods?
So it seems like these are all sort of hinging on these embeddings being in some sort of 3D space, which has a relatively easy distance metric. Does it work when you have to consider sort of the geodesic distance between any 2 points on a graph?
So you're talking about the geodesic distance instead of, for example, the Euclidean.
Yeah, so I guess sort of these applications are with molecules, which have sort of this nice physical space interpretation. But for the other sorts of graphs that you mentioned, getting sort of when there's not necessarily an easily definable Euclidean distance and angles and whatnot, does it work with a geodesic distance if you have, for example, edge weights?
Yeah, that's a good. Yeah, I think that's a very good point. So, I think that partially can be considered if you consider the number. If, for example, I extend this to 2 hop neighbors, basically you automatically consider the nodes that are 2 hops away. So this is some kind of geodesic distance. And I think if you want to consider geodesic, there is a there is a special kind of symmetry you need to consider. This is called the gauge symmetry, GAUG. I think there is a separate. I think people study this, for example, for proteins here, we can consider each residue as a node. Then you have a graph. But also you can consider, for example, consider it as an energy map. Then the protein will look like some kind of complicated shape. And then you need to consider, for example, the curvature, etc. And I think the gauge symmetry is what you can use. I think there's a paper by Michael Brostein's team, Nature Methods, I think last year. They developed some the gauge symmetry, gauge convolution by treating a protein as kind of an energy map.
I have a rudimentary question. What is the input to your learning algorithm? What is your output?
The input in the 3D graph, we have nodes and one each node, and the output is usually is the learned node level features, which can be used for node classification or regression, and it also contains graph level features, which can be used for graph regression or classification.
Yeah, I think that's a good question. So usually, I think the input is simply as Li said. So you basically you can concretely you can think about this as I have a node feature matrix. So for example, if I have n nodes, each node has an attribute of d dimension. You can put this into an n by d matrix. Each row is a node feature for each node, right? Then you also need to you also can have a connectivity matrix where you tell which node is connected, which node adjacency matrix. Then you need to also have a coordinate matrix. If you have n nodes, it's n by 3 matrix, given the telling you the coordinates of each node. So there, I think if we don't use pooling, so each when you do each update, basically you update only this feature matrix, this N by D matrix. So you given this graph, each update will consider neighbor, etc., to only update the feature matrix. So you will do whatever the number of layers you will do. So this number N will not change, but the D might change depending on the hidden representation, the length of hidden representation along this in this network. So the D might change, but N will not change. So so if you want to do finally, if you want to do after this so many layers, so if you want to do a node level prediction, you simply take this node representation and you predict the label for each row, right? Of this out of this N by D matrix. And if you want to do a graph level prediction, so you usually I think people will do some kind of people call the readout. Basically, you convert this. So in that case, you can do an average pooling. For example, you average this across all the nodes, and you get a representation for the entire graph, and then you can predict the property for the entire graph. But the reason why we're doing this is because if you do graph level prediction problem, the graph have different sizes. I can have 10 nodes, 15 nodes, 100 nodes. So the prediction should equally work. So that's why. So this intermediate representation will depend on the size, but you have to have a final readout layer where whatever number of input nodes you have to read out in a single vector.
So you have an X, which is a pretty complicated data structure, right? It's entire information of the graph.
Yeah.
That is not subject to change, right? That's
Right.
kind of been given to you.
Yeah.
And now you have a Y corresponding to that X.
Yeah.
So what is the Y structure? Y is a kind of a scalar, is a vector, is a matrix, how the Y looks like.
I think it's based on the downstream tasks. Usually it's a scalar for the whole graph or a scalar for one node. And sometimes it's a vector for each node.
Okay, so your task is you make a connection between the X and with the Y.
Yeah.
Right?
Yeah.
And now when there's a new X coming in, you basically said, okay, what is the corresponding Y for the new X?
Yeah, absolutely. Yeah. I think it depends on, that's what it depends on if you want to do, for example, a graph level prediction. Given a molecule, I want to predict yes or no. Then the output is simply, just a yes or no, 0, 1, right? So this is a graph level prediction. So if given a molecule, I want to predict if this molecule is antibiotic or not. Basically, given a graph, the output Y is yes or no, just like a binary classification problem. And if you want to do, for example, node level prediction, if you want to predict the label for each node, then whatever, if you have your input has 10 nodes, then output will be a 10-dimensional vector telling yes, no for each node. And if I think the equivariance case is more interesting. Because if you want to predict, for example, velocity for each node, I want to predict a velocity for each atom. Then, if you have so then the output will be N by 3, right? So each row will be a 3-dimensional vector. You have a prediction of 3-dimensional vector for each node representing the velocity.
Okay. So the invariant and the equivariant is basically additional constraint to make sure you don't really kind of predict two different things, even for the same,
right?
The human intelligible type of input.
Absolutely, yeah. Okay. So for example, if you rotate the molecule, the input will change, right? The coordinate will change, but your output should not change.
Just like in the image, right?
Yeah, exactly.
If you have a cat, kind of just rotate,
exactly.
It's still a cat.
Exactly. If you have a cat image of cat, if you rotate this image, to us it's the same image, so the output will not change. But for example, if you train a regular convolutional network, and if you have network trained, if you give the image and give a rotated version, the prediction will be different.
What about equivariant? What is the corresponding analogy for the cat?
So the
invariant is the rotation, the equivariant is what? It's a scaling?
Yeah.
What is the?
That's a very good question. So how equivariance can be visualized, for example, in the image case?
What is that?
I think, a simple example, for example, there's a cat in image, and maybe there's a vector from the head to the body of this cat.
There's a very easier way to explain that. I think that's a very good question. So then the task is different. So if you do image classification, this is invariance, right? If you rotate the image, translate the image, output should not change.
Even you scale the image.
Yeah. So the equivalence come, for example, if you do image segmentation, if you want to do a pixel-wise prediction, you want to make a prediction for each pixel. If you rotate the input, the output will be rotated, should be a rotated copy. Yeah, if you, for example, a segmentation task, you predict a label for each input pixel. So your output is basically a prediction map of same size as your input. So it's basically some 0-1 prediction, but the size is the same. So if you rotate your input, your output map should be rotated corresponding. Yeah.
So my last question, I promise. So when we are saying 3D here, we are pretty much exclusively considering spatial 3D. So we couldn't, for example, consider 2 space dimensions and a time dimension.
Dynamic 2D, right?
Right, so it's like, it's not just that we have 3 dimensions, it's that we have 3 dimensions, all of which are related in the same metric.
That is.
Yeah, I think that's a good question. Usually, I think because this 3D basically, most of them are in the physical world. So you have protein or whatever you have. We usually assume the 3D, the spatial dimension is 3D. If you consider time, I think you could, if you have something 2D like a video, right? It's basically each frame is 2D, but you have a time dimension.
Right, like a video, yeah.
Yeah, so in that case, I think ideally you should treat these 2 dimensions slightly different, right? Because they are not, ideally you can treat a video as a 3D image, but the other dimension is different with this XYs. So I think people usually do some kind of different processing along the temporal.
And I think this 3D, when we are talking about the equivariance, it means the equivalent to the rotation. So that rotation is under the SE3 group, the spatial Euclid group. So which corresponds to the 3D space we are living in.
You want to take a break now, or you want to do that later?
Yeah, how about we take a break for 5 minutes?
Okay,
It's already hot.
Okay, hello everyone. My name is Yu Jilo, and I'm a 4th year PhD student from Dr. Di's lab. So in the next part of this tutorial, I will introduce the graph generation, another research topic being covered by our DIG package. So in this graph generation problem, basically, we are trying to study the problem of generate known molecular graphs, either in 2D or 3D, using generation models. So our problem setting here is that we are given a molecular data set. So the molecules are in this data set in the form of 2D molecules or 3D molecules. Then we will train deep generation models on this data set, so that this trained generation model can capture the distribution of the molecular graph data in this data set. So then after we train this model, we use it to generate known molecules from the captured distribution scheme. Okay, so actually this problem has many real world applications. Like if you want to develop a generation model that can help you discover novel molecules or novel drug molecules. You don't know what is the molecule you want, but you like this generating models to help you discover or generate this molecule. So that can be a very potential application scenarios that you can use to set in this program to solve the task. Okay, so here the 2D molecule graph, I mean, is like the molecule graph that only contains the topology information in the molecule. See that you only have nodes and edges in the graph, and the nodes correspond to atoms in the molecule, and edges correspond to bonds in the molecule. And the 3D molecule graphs, see, I think you have already listened here let's talk their graphs that each node in the graph is associated with a 3D coordinate corresponding to the atoms 3D position in this 3D space. Okay, so that is the program settings. And to solve this problem, actually, we have a lot of challenges. So first, what we are dealing with in this program is actually non-grid data. So you know there are a lot of data that has some regular grid-like form, meaning that their organization in this data structure is regular, have a grid-like structure. So a very intuitive example is images. Okay, so image is like a regular tensor or matrices, you know, how very regular grid points, well organized and concrete defined patterns. Graphs, they are different. You have nodes, you have edges, but these nodes can be arbitrarily connected, okay, by edges. So they do not have like such grid-like structures. Whatever you are dealing with is 2D graph or 3D graph. So that is a very significant challenge to use deep generative models to capture the distribution and generate this kind of complicated data. The second challenge lies in that if you are dealing with 2D molecular graphs, so you are facing the problem of generating the nodes, the edges in the graph, but you know the nodes, edges, they are discrete instances, so whatever, you know, like the nodes, they are categorical discrete numbers, carbon atom, nitrogen atom, or etc. To have categorical types, they are discrete numbers. Also the edges, single bonds, double bonds, they are categorical numbers. So you need this generative model to capture discrete distribution. And thirdly, if you are dealing with 3D molecular graph generation, I think you have already know like the invariance, equivalence, these concepts from the former part of this lecture. And also this problem exists in graph generation of the 3D molecular graph. You also need this generative model to achieve invariance to SC3 transformations, including rotation and translation. So we know that a lot of different generative models have been proposed in the recent years or decades, like from the traditional generative models, including GAN, VAE models used for image generation, and deep autoregressive model used for text generation, and a very theoretical solid model, energy-based model. And if you have some experience in creating some apps and you include a sentence, then you can get an image. And actually the core engine behind these apps in image generation is diffusion model. They're very hot and popular in recent years. Okay, so we can find that most of these models actually are trying to build a mapping between the data X and the latent variable Z here. Okay, so what generative models are doing is just you give one data sample, then in the training, usually I do inference, mapping this data sample to the latent variable Z here. And actually in the training, I would like to map latent variable Z's distribution is close to some prior distribution. Usually use Gaussian distribution. And when the model is trained, you're doing the inverse direction. You first sample this latent variable Z from the prior distribution, then you map it back to the data. Actually, you are just in this process generating some new data samples. Okay, so that is working flow of generative models. And generative models have been widely used to generate like images, texts, music, etc. And also, of course, they have been used in graph generation. Okay, so I list some methods here in recent years proposed by different researchers using different styles of generation. So we can generate graphs either in like atom by atom style generation, or in motif by motif style generation, or by one shot, just in generate everything in one shot mapping. Okay, so and also you can use very different generative models you can list a table of distribution generating methods. But in our tutorial here, we will focus on 3 methods. So these 2 methods are using flow models and atom by atom style generation to generate the molecules. Graph DF is generating 2D molecule graph, and GSFIRNet generating 3D molecule graphs. And finally, very recent method called EDM, the generating 3D molecule graphs using diffusion models. Okay, so let's start from the first method. So graph DF, it is a known method using flow models and discrete latent variables for 2D molecular graph generation. So in this method, we are using flow models. The generation pipeline of the flow models is actually shown in this figure here. So in the training, as I said, we do the inference. So we include the data X for the model here, and then we get the latent variable G here. And so then what is typical and significant feature in flow models is that their designs in the mapping between the data X and the latent variable Z is invertible. So meaning that you can always find an invertible mapping of your model F theta to exactly map this latent Z back to your input data X. Okay, so this feature allows you to do the exact likelihood computation using the change of variable theorem in statistics. Okay, so actually in the training of the flow models, you try to assume this outputted J is subjected to Gaussian distribution or other prior distribution. Then you compute the likelihood of your data X for every data sample in the data set, and you maximize this likelihood. Okay, then in the generation, you sample G from the prior distribution and use the invertible of this, use the inversion direction of your model to get it back to the new data samples. Okay,
So is here your vector Z of the same dimension of vector X?
yes.
It's guaranteed to be the same.
Yeah,
Has to
yeah.
be the same. Okay.
Yeah. Okay, so but the general flow models are designed for like continuous numbers or vectors or variables or whatever. So mean X and Z here are continuous numbers. But we are dealing with like a graph structure. So how can we use flow models to generate such graph structures? So we need to do several things to make the flow model suitable for graph generation problem. So first, we need to like convert this overall graph structure to a sequence of discrete tokens. Okay, usually we may use some Chalmers algorithm to process your graphs in the graph data set. You can get a Chalmers order. Actually, you assume it to be the generation order of when using your models to generate this graph in the data set. Okay, so for example, here I generate a molecule with 1 carbon, 1 oxygen, and 1 nitrogen atom. So maybe I first generate a carbon atom, then generate the oxygen atom, and generate the bond connecting this carbon and oxygen atom. Then I generate the last nitrogen atom, and generating the bonds, edges connecting the previously 2 generated atoms. So I get an order and can then decompose the molecular graph into a sequence of discrete tokens here. So the AI here means the ith atom, the type of the ith atom that I will generate in the sequential generation process, and Bij means the edge between the ith and jth atom that I will generate in the sequential generation process. So the generation is sequential. You generate 1 discrete token at each step. Okay, so that is the way you convert the graph to a discrete sequence. Then you need to also additionally you need to make some modification to the flow models to make it suitable to capture the discrete distribution in the tokens or the sequence that you will generate. Okay, so what we do here is in graph DF method is we use the discrete autoregressive flow model to map the discrete latent variables Z to the next discrete token that you will generate in each step. Okay, whatever X is node type or edge type, but you use the flow models to map discrete latent variable Z to the token X. And this model is composed of multiple invertible module shift transformations. So we use these types of transformation here to do like the mapping each layer of the model. So this formula can be written as X equals Z plus mu module T here. So in this formula, the Z is the input, the X is output. Okay, so the mu is captures the conditional information. So meaning that in each step of generation, you will always condition on the things that you have generated in previous steps. Okay, and T is the number of categories of the X that you will be generated. Okay, so you stack in multiple of such module shift transformation based layer to do the generation and running it in multi-time steps. So you can then completely generate the complete sequence and then you can use it to form a graph structure. Okay, so that is the working timeline of graph DF method.
Okay, so I have a question here. I don't quite get the point. So it looks like in order to generate the graph, you need a Z to start with, right? If I have an X, that's already a graph.
Yeah.
So I don't have an X, I have a Z, and I need to generate a new graph. Is that right?
Yeah.
Okay, so in order to describe the graph, the X is pretty complicated, like Dr. G just mentioned, right? It's really complicated.
Yeah.
So in order to have that X, I need to have a Z as complicated as X. Now I understand the motivation to say, suppose I have this property of X, Y, Z, I need to want to know what kind of molecule structure to produce this kind of property. But if you say, give me a kind of complicated data structure, therefore I can generate a graph for you. I don't know that in the first place, do you? You understand my concern?
So your question is about like you want to generate graphs with some properties.
No, I don't quite understand why people want to do something like this. To have a Z to generate an X, but the Z should be as complicated as X.
A good question. Yeah, actually, what we are doing here maybe like in basic generally generative models is we want to fundamentally we want to learn some distribution in the model, right? Because we do not know the distribution, what is the exact distribution in the data, right? You are just giving me a data set, but I do not know the distribution of it. Once I know the distribution, of course, I can sample from it and then I generate a new sample. It's okay. But the problem is I do not know. So then I want the model to learn this distribution. Okay. So how I capture this distribution? Actually, I cannot manage the model to tell me the formula of the distribution. But I have to use something implicitly to capture distributions. But see here, so whatever, like the given diffusion model, whatever, Z is latent variables.
But it depends on the usefulness, depends on how easy to get the Z, right? I appreciate this part. I think it helps. You said we need to have the distribution, right? The FX, right? That kind of give you a kind of ability. Once you give a Z, you can inverse and then generate the X prime, right?
Yeah.
Like in autoencoder type of things, usually the Z is much smaller than X.
Yeah.
Right. So if I have 200 dimension of X, 2000 dimension of X, I only have 3Z. And now once I specify the 3Z, they give me an X prime, which is of the same dimension of X. But here you said that the flow model, the Z is of the same size of X.
Yeah.
So your graph here, the Z is much shorter. Actually, it's not really that shorter, right? It's actually the same height of X. So in order to generate the X prime, I need to start with the 2000 dimension Z. Realistically, in real life, how do I know that 2000 dimension Z? Do you think that's a real problem?
So
But first, for flow model, we need Z to be same dimension as X. Is that required?
Yes.
It's required, just like in diffusion. I know in diffusion they have to be.
So would it be similar in some sense to say that X and Z might have the same dimension? And the distribution on X is potentially very complicated and hard to express, but we can assume that the distribution on Z is potentially very simple, like a multivariate independent normal.
Exactly.
And by assuming that at the outset, we can say, once we can find a way to transform X into an independent normal, we can do a reverse of that transformation to take independent normal samples and generate X.
That's
So you basically will artificially generate the Z by using individual, almost random noise assembled together.
Yes.
And then to use that to generate a meaningful X prime.
Yes.
Yeah.
Yes, of course.
So that's-
Even not a kind of a contrary message to garbage in, garbage out type of thing. So you basically said, I have such a magic machine. If I give a garbage in, I have
Yeah, that's
something meaningful out.
Yeah, that's a great question. So I think, so there is a theorem in statistics says, if I have a sufficiently complicated neural network, etc., I can transform a complicated distribution, any distribution into a standard Gaussian, right? So we know that there is such a theorem. I can basically, I have a very complicated distribution here. If I use a sufficient complex neural network or complex function, I can convert that distribution into a standard Gaussian. Zero mean unit variance.
There are some conditions on what that
Yeah.
distribution is, but
Yeah. So there is more or less some kind of a theorem like that. So, for example, I think the easiest way to explain this is if you use VAE, and what's the difference between VAE versus AE autoencoder, right? VAE is a variational autoencoder. Relationship between that, I think, is in autoencoder, we all know, right? It's just the encoder get a little smaller hidden node than the decoder. So the variational here is you also, on top of that, you also require the Z to follow a prior distribution like a standard Gaussian.
I somewhat disagree with that characterization. I think the VAE part, the Z is not entirely meaningless, right? If a three independent Gaussian variable, to me, it's just a kind of random noise put together. Here, the Z is kind of a lower dimension representation of the X, right? Basically said there's a lot of redundant information in X. The essence of that is captured by Z, right? That Z is of much lower dimension. They shouldn't be entirely of a univariate normal distribution independent from each other. Because if you reduce that X into that Z, basically the information, all the useful information lost.
But I think the key is that something during that process, you learn something in the encoder.
Right, but in the end, the information stored in Z shouldn't be in completely independent univariate normal distribution. If that's the case, it's almost you give anyone a kind of random noise, they're going to just recover.
Yeah,
that's really kind of indeterminate mathematical problem. No?
Yeah, I think the key also here is in training. Given this, you need to do a decoder, and you need to reconstruct that input.
Right.
So although here it's more like standard Gaussian, you can.
No, that's the part I disagree. I don't think the Z can be standard Gaussian. Because once the Z becomes standard Gaussian, you can generate a unique, meaningful X prime back. It's really kind of defy the entropy theory.
It might be that standard independent Gaussian is a bit of a simplification. Something like a Gaussian process might be more realistic, in which once you can condition on the first input, you can follow a Gibbs procedure to generate sort of collapse.
Nonetheless, the Z should capture the essence in that X, right? Otherwise, the information flow doesn't really kind of click.
Yeah.
Because you give different kind of X, the Z should be different. Otherwise, how can you generate a meaningful X prime? If you give any kind of different X, it get the same Z. How do you differentiate?
I think that you do end up having some, because you're only considering as a prior, once you sort of, the likelihood in some sense is the output of these different flows which you're learning. And then you end up with some sort of posterior. And I think that that inverse transformation is sort of capturing that posterior information in order to draw your samples. So it's almost like a rejection sampling type of deal, where you can assume sort of your proposal distribution is maybe something like a standard Gaussian process model. And then based on that, and the information you learn from F, you sort of get samples from your posterior and some approximate.
In that case, you don't really need the Z anymore, right? You basically just need the fx or the inverse of that distribution.
Right, except it can be very challenging to draw from complicated distributions, whereas it's relatively straightforward to draw from something like a normal or a Gaussian process.
Another reason is the data distribution is usually unknown. So we have to map it to a prior low-end distribution, latent distribution, like a Gaussian distribution.
That part I agree, but in the flow model, you are not really mapping to a lower end. You're basically of the same dimension, right?
It is follow a prior Gaussian distribution.
Yeah.
So you can sample from it, but for original data space X, we don't know the underlying data distribution, so we cannot sample from the P of X, but we can sample from P of Z.
It's almost like doing.
I know Dr. James, hazarding, I don't have an answer. Actually, yeah. So if we need to have any relationship between these two, do we need to have some parameter sharing exactly in the two parts?
Of course, I think
No,
In VAE, no, I think, right?
no.
In flow model, yes. I think, if yes, I think that might be some answer to your question, right?
VAE encoder and decoder do not show any.
They do not share, I think they do not share.
okay. So that would be to your answer to that, right? If they don't share, well, assume from your interpretation, they have to share some of that to take the information processing in the encoding part. Otherwise,
Yeah, I think probably this is also the same question as Dr. Ding asked. In training, can I just remove this part? And can I just because this is a standard Gaussian. And I know, can I just generate sample Z and do decoder part? Can I just remove this part even in training? Right? Because I think Dr. James, and so if you have some data, you encode into a standard Gaussian and all the information is lost. You just basically a sample here and generate. Can I just remove this part completely?
right.
Right?
We cannot, because the loss function is defined by the reconstruction between X prime and X, the distance.
You are talking about the technical part.
Yeah,
If you think about it from a conceptual part, right?
VAE is like doing something like minimize like some lower bound of the likelihood of distribution, likelihood of the X. Okay, so this lower bound is composed of reconstruction and regularization loss on Z. Regularization loss on Z pushes this distribution of Z close to standard Gaussian distribution, and the reconstruction loss pushes you to exactly reconstruct X in this X prime. So you have to combine these two loss functions, and actually this is the theorem of relational inference. I think in statistics.
That's what I meant to mention, is that in a variational standpoint, it seems sort of like what you're doing is trying to minimize the KL divergence from some known family on Z, probably some sort of Gaussian related family, and then some complicated family which you don't have a close form expression for, but you can minimize some elbow in order to get close to it.
Yes, so I guess like Dr. is concerning like the origin, whatever process is origin by mapping X to Z and Z is standard Gaussian distribution origin, you lost information.
That's not my initial concern. My initial concern was really how you're going to use that flow model, right? Because the Z is of same dimension. When you try to answer the question, you said that Z actually can be easily generated from independent standard normal distribution.
Yes.
To me, that's really kind of collection of noise, right? And then from that, you can really kind of produce a meaningful X prime. That's surprising.
Yes. Yes.
So that's the part. Okay, I think we don't have to drag two lines and continue.
Okay. Okay, so maybe I can start from this second method. I will introduce this Shuiwang method. So this Shuiwang method is novel method used in like the autoregressive zoom models for 3D molecular graph generation. Okay, note that different from the graph DF method I introduced previously, we are not dealing with 3D molecular graphs. Okay, we have coordinates associated to the nodes in the graph. So our model will need to generate these 3D coordinates of atoms. So their capture distributions should be invariant to rotation and translation for the SC3 transformations. So in the Shuiwang method, we still use autoregressive or sequential generation pipeline here as atom by atom adding to the graph. So we completed it by many steps to form a complete molecular graphs. So exactly in this method, we are starting from one carbon atom. The next step, in each step, we generate the atom type AI and the 3D coordinate RI of the new atom sequentially by the autoregressive zoom models. Okay, so the generation of atom coordinates needs to satisfy the equivalence and the invariance property actually, because of you need to capture the SC3 invariant distributions. So the equivalence and invariance properties are actually illustrated here in this figure. So assume that in the complete like sequential generation step, you have already generated this subgraph, this molecule with 3 atoms here, okay? Then you will need to next generate this new atom with the atom type AI and the coordinate small I. And assume you have already generated this subgraph with the coordinate matrices big Ri. Okay, so assume in another round, okay, you are generating this, you have already generated this graph with big Gi prime. So actually this big Gi prime is the molecule that is rotated and translated of this in the last rounds generated big Gi. Okay, so their coordinate are actually is rotated by Q and translated by B here. So you still want to generate the next new atom. Okay, so to capture this distribution to be invariant to SC3 transformations of rotation and translation, actually you need to satisfy these 2 equations in your model and in your probabilistic model. So the first is actually assume your model will generate the new atom's coordinate as the small I. Then if your input condition of originally generated molecule is rotated and translated, then your model should also output the new coordinate as the rotated and translated ones corresponding to your originally generated new coordinate. Okay, so meaning that your output, that is the coordinate for the new atom to be generated, should always be equivalent to the input of the old coordinates of your already generated atoms. Okay, so that's the equivalence. And the invariance is just simply this probability distribution should be same as generating the correspondingly rotated and translated coordinate is exactly the same as generating this original one. Okay, so whatever I means is that in this sequential generation process, your generation should always like in the generation, the output is equivalent, and in the probabilistic modeling, this probability should always be invariant. So that is a key problem that you will face if you are using like such a sequential generation pipeline to generate a 3D molecule. So our idea is that we do not directly use the generative models to generate the coordinate I, because it is hard for now to like maintain this symmetry property. But instead, our method is proposed to generate the relative position to a focal atom in the form of the distance d angle theta and the torsion angle phi here. Okay, so this distance angles and torsion angles actually they are invariant to SC3 invariant transformations like because whatever you rotate, you translate in the 3D space. Actually, this distance, angles, torsion angles, keep the same for the same molecule, right? So they do not change as you do any rotation or translation in 3D space. So we select them as the generation target, and also to like maintain the invariance, like in this probabilistic modeling, our backbone network uses the SD3 invariant model SphereNet as the backbone network. So, and we also generate this SD3 invariant targets as the outputs. Okay, so because like all these designs are using SD3 invariant network and select this SD3 invariant targets as the generative models output, our models here can naturally satisfy the invariance and equivalence properties. Okay, so that is SphereNet method. And finally, I will introduce one short method for generating the 3D molecular graph, and it is proposed very recently, published last year. So actually, this method uses the very popular and hot generative models, diffusion models as the engine to generate 3D molecular graphs. So let's let me give a very short backup about this diffusion models theory. So a diffusion models actually defines the mapping between actually the same as other generative models, the mapping between the latent variable z and the data point x by two diffusion processes, forward and reverse diffusion process. So the forward diffusion process is you are sampling from this distribution step by step. Okay, so this x0 is the data sample from the data set. So this x capital T here is you can consider it as just the latent variable z. Okay, so you from x to the z, you are doing the forward diffusion and you step by step sampling from the diffusion. It's actually equivalent to you are always at a small level of Gaussian noise at each step. So this is exactly the diffusion process in physics. And after many steps of adding Gaussian noise, this big T can be very large, like thousands. Okay, then you finally obtain X big T here is the distribution of field is very close to the standard Gaussian distribution. You can consider it like some noise. Okay, so this actually this is like manually defined mapping from the X to Z, and the theory of the diffusion naturally maintains that your obtained latent variable Z is subject to Gaussian distribution. Okay, so in the generation, we're doing the reverse direction. We're sampling this Z here from the standard Gaussian distribution, and we want to turn this noise back to this meaningful image or data. But here we do not use manually defined some process. We are approximating the distribution by a model. Okay, so this model is actually trying to denoise the signal at each step from xt to xt minus 1. It tries to remove the noise and recover the meaningful patterns in the data. Okay, so naturally this x0 and x big T or x and z also has the same dimension here.
So here is a good example to our previous discussion, right?
Yeah.
So my question is this xt, this image is a very heavy noise, but the image is still there.
Yeah.
You need to remove the noise, basically shoot the image. Or is the xt purely just a noise? There's no image.
I believe it's
There's the
image. Yeah.
Okay, just like a water, right? If you hang a little rock at the bottom of here, you put a lot of water, you probably don't see the rock. But once you get over the water, you see the rock. Or is it just a pure water? There's no rock over there. But once you do some magic over there, there's a rock appear. So here you said basically there's an image over there, right?
Yeah, this.
So that I think that's my understanding too. The Z, previously, whatever you created, that Z cannot be pure noise. right? Even the noise component is bigger, probably overwhelm whatever the true signal. But if you get rid of the true signal and start with the pure noise, it's very hard to believe that can be recovered into a signal. Because I'm not sure, I'm not really familiar with the signal product, but here isn't that a kind of similar type of analogy?
Yeah, we actually the same.
Okay.
Yeah, because so this of course they have to be overwhelmed by noise.
Right,
Yeah,
right.
actually, but they at least have some information.
Right.
Overwhelmed noise makes the distribution close to like standard Gaussian distribution, so you can sample. Yeah. But it's
That part I understand, but that's a little bit kind of different story, right? It's just like, when we were little, when we have this kind of radio things, you need to tune very precisely to that channel, and then you start hear the news broadcast. Otherwise, it's static noise. Velocity is slightly away from that, right? So basically, it's like that is a manual process. How do you kind of get rid of the noise by tuning to that exactly channel? So here, of course, you need different kind of, but there's a signal over there. Otherwise, you are not able to just create a signal from this.
at least the model how to use the signal, so
Okay.
we try to recover the signal.
Okay, okay.
Okay, so like what I have mentioned before is like the standard diffusion model for image generation. So it is very natural. You just add Gaussian noise to the image pixel values and then recover it. You do not have to do any other chips. But here we are dealing with the 3D molecular graphs. Okay, we are dealing with trying to generate the 3D coordinates of atoms. So still in this method, they perturb the 3D molecule structure by Gaussian noise to atom coordinates. You can assume that you have a regular molecules and in this noise you can get a very noisy molecule structure, and then in the reverse direction, you try to use these diffusion models to predict the denoising vectors. Okay, that can map this perturbed 3D structure back to this original structure. Okay, so whatever the basic pipeline is the same. You add noise to perturb and you let the model to denoise these structures. But we have to capture the SD3 invariant distributions as I mentioned. So in these generative models. So to maintain these SD3 invariant distributions, the EDM method uses these two tricks to make sure that this invariant and symmetry are maintained. So the first trick is that they use the EGN model as the backbone network. So as Lina has introduced as a type of equivalent graph neural network models as the backbone model of the diffusion model. And then importantly, they always zero center these 3D structures so that they can remove the degree of freedom from translation. Actually translation in the 3D space, but I always zero center the structures, whatever structure in the data set or the intermediately generated structure, whatever, I always zero center them so that maintain that this distribution is always built upon structures that have zero centroids. Okay, so then I can cancel out the degree of freedom from translation. Okay, so by using these two strategies, using GNN, always output a rotation equivalent noise vector and always zero centering, and cancel out the transformation, the degree of freedom from translation. So then these models will always capture the SD3 invariant distribution in diffusion models and can be successfully applied to the problem of 3D molecular graph generation. Okay, so that's all about the methods that I will introduce in this tutorial. And actually, there are a lot of frontier applications of molecular graph generation problem. Like one, the method that I have introduced today is about the unconditional generation, meaning that I do not take any condition information as input and just generate graphs from scratch. Actually, there are a lot of applications that requires you to take some conditional information. Like one problem is you generate the structure from the conditional 2D graph. And the other problem setting may be like you take the protein, take the target protein as a conditional input, and you are required to generate some 3D molecule structure that can bind to this protein property. So these are also very interesting applications, and a lot of works and studies have been done for these types of problems. Okay, so that's my part for this tutorial. Yeah. Thank you. Any other questions?
Yeah, I will go through the last part of our tutorial. So this part is basically a hands-on session for using our DIG library. So yeah, if you have a laptop, if you want to go through the code with us, you can just Google dive into graphs, our library name. So basically this is the GitHub homepage of our library, and on this page you can find everything about our library. So basically this library dive into graphs is a software for graph deep learning research. So in this library, we covered several directions of graph deep learning research. It includes the 2 directions we introduced today, like graph generation and deep learning on 3D graphs. And we also have the directions we introduced in our part 1, self-supervised learning on graphs and the explainability. And also we have a graph out of distribution direction for in this library. So for each research direction, in this library we implemented the data interfaces for the commonly used data set in the community, and we have the popular algorithms implemented as well. And also we have the API for evaluation. So basically, if you want to do research for these directions, you can use our library to benchmark algorithms and implement your own algorithm and compare with baselines. Okay, so today our demo code is attached here. Colab demo. You can if you open this, basically you go to you go to a Google Colab. I open it here. So we can make a copy of this notebook. So let's see, file and save a copy in Google Drive, and then it will create a copy of this demo code. So we can clear the results we get previously. So edit, there is a clear all outputs. Yeah. So basically, for this demo code, we have 3 parts. The first part is to set up the environment for our library. And then I will have a very simple demo to show how to perform a deep learning method, basically SphereNet, as we introduced before, on 3D graphs. And also we have a demo code for graph generation. Okay, so the organization of our library is very near. So we have 5 directions, and each direction has its own subdirectory in our software. So our software name is DIG, and for graph generation we have dig.ggraph, and for self-supervised learning we have dig.ssl graph, and etc. So for 3D graphs we have dig.3dgraph. Okay, yeah. So the first step is to set up an environment for our library. So our library is based on 2 dependencies. The first one is PyTorch. So I attached the link here. So basically, PyTorch is a library for deep learning. Basically, you can implement like models, your data loader or evaluation metrics based on PyTorch, and you can run the training on like common devices like CPU or GPU. So we can install PyTorch by running this line of code. So basically people install Torch. Yeah, I need to wait a second because it is initializing the kernel. Yeah, I run this demo code on Colab because it provides us a clean environment, so you don't have to set up the environment on your local machine or your server. So you just do this online. So our DIG library requires a PyTorch version newer than 1.10. Okay, so we can check the Torch version. So currently, I think it's 1.18 or something. 2. Is 2.0. So, and you can see the CUDA version provided by this Colab is 11. Okay, and the second dependency of our library is PyTorch geometry. I attached the link here. So if you are interested in graph deep learning, I think the PyTorch geometry is a very good library. Basically, it is an extension library of PyTorch, and it focuses on graph data. So it provides some implementations you can see from their document, some basic component of graph neural networks, and some data loader and data augmentation, transformation, or some utility functions. So our DIG library has many use many APIs from PyTorch geometry. So we can install PyTorch geometry by using this line of code, and you can also follow their instruction to install it on your local machine based on your own environment. But on this online Colab, we just use this line pip install Torch geometry, and we also install some other dependencies. Okay, we can check the version. Yeah, so that's all for the environment we need to use our DIG library. Do you have any questions or problems to run this code?
Do you need a GPU to run it?
Yeah, so if you want to do this on your own local machine, you do need it. But if you just run it use Colab, we don't need it, because Colab is basically a service provided by Google. It provides you like remote GPU or TPU. But its free version is very limited. It only provides like a limited memory for GPU. And you can also like purchase their Colab Pro, and it provides you large memory and more GPU or TPUs.
What if a student wants to use it on the HPRC machine? How do can they do that?
So HPRC is a computer center.
Yeah. So the high performance computing for Texas A&M. So they
think-
have a GPU on those machines.
Oh, okay. They do have a GPU or just CPU in
They
the.
have a GPU.
I think they. Sorry, one second. I think they do have like if they have GPU, I think we can use it. But these GPUs are provided by Google for educational purpose.
Do you all have like a Docker file or Singularity image that students could take and put onto the HPRC to use it?
We currently don't have that for the specific computing center, but we do have an instruction for. You can check this is our homepage, and we have a documentation, and we also have a installation instruction on our homepage. So basically, our environment is quite simple. The dependencies are only two things: PyTorch and PyTorch geometry. So the users just need to install the corresponding version of PyTorch and PyTorch geometry based on their version type, like the CUDA version or the, yeah, basically just the CUDA version, I think is the key.
Right, I was more asking, is there a, because for the HPRC at least, there's sort of a very limited number of files that you can keep in your home directory. And I don't believe that there's sort of a module that would necessarily guarantee those versions, but if you have like a Docker file or something, they have a permissionless container version that you can run.
We can check it out, because in our lab, we do not use switch, so we're not familiar with that. So usually we just use like servers, there are GPUs on that, and we can install those versions based on our version. But we can definitely check that if you want to install that on that machine.
I think that's a good point, because for a lot of non-computer science people, in order to use beyond the educational knowledge, right? They have to use HPRC for running on the standard package. Everything I think is available through their pre-installed. I don't think you have a lot of privilege to install anything over there, right? How to use that, right? Because the controller very tight. You have to submit a job and run that. And then if you need something, you can tell the administrator to say, I need to install this one. They may or may not agree to.
About this container, as long as you can run it as a permissionless container,
Okay.
you can submit it to the HPRC and not have to worry about those types of library dependencies.
Okay, I think we do. We think we can provide a Docker image for that case.
Right.
Yeah, if you need.
Yeah.
And then if you just want to play some easy code, you can just use Colab. Is very, because usually if you have a local machine, it is suffering to install specific environment. Usually the different versions, different dependencies. A Colab really provides you very general purpose backend, so it's very convenient to set up the environment with simple several lines of code of comments. Okay, so this is the first part, which we set up the dependencies. So I will show a demo for deep learning on 3D graphs. So basically, as Lima introduced, we have many models for learning from 3D graphs. So our input is a 3D graph with coordinates, and we want to predict some properties of this input graph. So specifically in this example, we use the experiments on QM9 dataset. So this QM9 dataset is the quantum molecular property dataset. For each molecule, 3D molecule, we have like 12 properties for that molecule, like the energies or the homonormal gap, but basically some chemical properties. So, so as shown in this table, we have 12 targets or labels for each molecule, and we train for each property, we train an individual model. And in this demo, we show one model for a specific property. Okay, so the first step is to import the dependencies. We need to import PyTorch, and we need to import our DIG library. Specifically, I haven't installed DIG yet. Sorry, I forgot the last step. We need to install our own library to install DIG graphs. Let me check the version. I guess it's our newest version, 1.1.0. So we need to import the APIs. So for 3D graphs, we provide the dataset API. Basically, you can check the documentation of our library. It provides the detailed explanation of every API. So for 3D part, you can see we have DIG, 3D graph, dataset, here, DIG 3D graph dataset, DIG 3D graph method and evaluation and utility functions. So for dataset, we provide the dataset API for commonly used dataset in the community. So in this tutorial, we import the QM9 3D. And also we import some method spherelet we implemented in the library and the evaluation metrics. And the run method is basically a training group for this method. And we can check the device provided by Colab. It's a CUDA, it's a GPU basically. So the first step, the following step is to load the data set. So it is very simple. Since we already import the QM9 3D data set, we can just load the data set by calling this API. So we just call we just need to pass it argument, the root. So the root basically is the directory you want to store the data set. So we can create a data set here. And our target in this example is U0. U0 means the energy of the molecule. Since there are 12 targets for this data set, we only need to load one of them to train our specific model. So our label Y is extracted from this target. And also we have the split indices for each, for the training set, validation set, and test set. So we just call the get index split method to get the data set splits. So we can run this to load the data set. You can say it will download the data set to your memory. So on Colab, you have like a temporary memory, so you will download to that. So we just need to write several lines of code to load the data set by using DIG. Yeah, and after we load the data set, our next step is to define the model. What Nime has described. In this example, we will use the spherelet. So basically, it takes the 3D graphs as input, and for each node, we will update the node representations by using the neighboring nodes. During this updating, we need to consider the distance angles, torsion angles into the message passing schema. So in our DIG library, we provide the implementation for spherelet. So we just need to call this class we defined to initialize the model, and we need to pass some arguments for this model, like the hidden dimensions, number of layers, or like number of basis functions we use. So we just pass these arguments to the class, and we can define this model. And we also define the loss function to train the model as the L1 loss. Basically, it is the L1 distance between the model output and the label given by the dataset. And also define the evaluator, which was imported from our 3D graphs evaluator. Okay. Yeah, our next step is to train the model and evaluating the output of the model. So we just call the run method and pass the dataset, the training dataset, validation, and test dataset into the method, and define the model and define class function, evaluator, and some hyperparameters, like the number of epochs you want to train, like batch size, learning rate, and the learning rate PK factor. So we pass all this to the run method, and we can start training the model. So due to the time issue, I only show one epoch of the training. You can see after we start this training, it is so you can see the batch size is 32. So for each epoch, we will train like each epoch can be divided into over 3,000 batches. So usually it takes several minutes to train spherelet on QM9 with a regular GPU. Yeah, we can wait it here, but we can move to the following code. Yeah, and also if you just want to use the model to do prediction, you don't want to train it by yourself, you can download this model from this link. We pre-trained some model, so you don't have to train the model from scratch if you just want to use the trained model to predict some properties. Okay, so that's all for the 3D deep learning, the deep learning on 3D graphs. Do you have any questions on this? Yeah, I think for the graph generation part, we cannot run it here because the memory given by Colab is very limited. This data set for graph generation is very large, so we cannot download it to this memory. But I also show the code here. And if you are interested in the running results, you can check our GitHub homepage. You can go to tutorials. You can see we have tutorials for each direction, and go to graph generation part. You can check our previously running results on this on graph generation. So basically, the steps are quite similar. The first step is to load the data set defined by our defined in our library, and we use the implemented GraphDF API to define the model and we train the model. After we train the model, we can use it to generate new molecules, and then use the evaluator to evaluate some certain properties of the generated results, like the valid ratio of the generated molecules, the log ratio of the generated molecules. And also we have a pre-trained model. If you are just using it to predict, you can just use our pre-trained models. Yeah, I think that's all for the demo code part. Yeah, you can play around with this demo code and our example code, and if you have any issues, you can post them to our GitHub issue discussion chat.